So let us simulate multi-stage sorry. So let us simulate Darlington amplifier. Let us simulate a Darlington amplifier. So where design of the Darlington amplifier is will be similar with the common collector amplifier, which we have done in the previous session. So what I do is, based on the operating point of the two transistors, I will be observing the value of this one, which is around like 2.2, which I have it availability, which I have availability with in the lab. Based on that, I choose this much, and I will be using a voltage requirement of this one. Need around 0.7 over here, need 0.7 over here, and I need some amount of the voltage around 6 volts. So based on these three requirements, 0.7 plus 0.7 plus 6, it is around 7.4 volts requirement. So based on the voltage requirement, I have adjusted this one, and I observed that the resistance need to be of 1 mega ohms over here, 1.5 mega ohms over here. And after I do the connections, so here I have to simulate my Darlington amplifier, and I have to observe few things where I have to verify the voltage gain should be 1. It is almost less than or equal to 1, and current gain AI should be maximum. So practically through observation, the transistor over here, it will be taking like IB. It will be taking IB, and it will be amplifying over here, and will generate the current over here 1 plus HFE times of IB, or in few cases we represent beta HFE in place of beta. So it will be 1 plus beta times of IB, and approximately beta times of IB. So when beta times of IB flow over here, so there will be again beta times of the current, which I pass it around beta times of IB. So that much again beta times of IB. So that much current will be expected by the transistor. So now there will be output current of how much? It's around beta square times of IB. So output by input, if you see, there will be HFE whole square times or beta whole square times. So I can say the current gain is nothing but beta whole square or HFE whole square. So that's all. That's what I have to verify. And coming to third one, that input resistance of my Darlington pair. So we call this one is CC followed by CC. So input resistance of a common collector followed by common collector Darlington amplifier should be maximum. So the maximum value of the input resistance, let me calculate it over here. So there will be 2.2 times of the resistance offered by this one. So effective resistance of this one, once I bring it to this branch, there will be beta whole square times beta times I have to scale. So 2.2 kilo ohms, it will be multiplied with a beta. So then a current scaling will be satisfied. So that resistance at this point, it will be that RE resistance of this much. So here beta times of RE. So if the same resistance, if I bring it to this one, so beta whole square times of RE. So now from this point to a ground, I can see there will be a resistance of beta whole square times of RE, and from the same point to the ground, I can see there will be this resistance also connected, and this resistance also will be connected. Once we do the AC analysis, that VCC will be connected to the ground. So from this point, so there is a input resistance, I can write it theoretically. So there will be R1 parallel with R2 parallel with R input of my Darlington amplifier. The effective resistance is around beta whole square times of RE parallel with R1 calculated value is around like 1 mega, and parallel with 1.5 mega, and parallel with the beta square times of Re. So beta square in the sense is like I consider the beta value of the transistor is around 100. So 100 whole square, it will be 10 to the power of 4 times of 2.2 kilo ohms. So it's around like 22 mega ohms. So all around this, if I write it, so 22 mega ohms. So now if I calculate this one, so 1 mega parallel with 1.5, by 2.5, it is around 0.6 mega parallel with 22 mega. If I write it into 22 divided by, so 22.6, it's around so 584 kilo ohms. So now I have to prove that the input resistance is maximum around 584 kilo ohms. So these three things need to be verified, and meanwhile I have to verify one more thing. The phase shift offered by this one should be 0 degrees. So the comparison point of view, what we have to do is, so comparison point of view, if I observe this one with a CE amplifier and a CC amplifier, so the phase shift for this one is 0 degrees for this one, and 180 degrees for this one. And we have observed already in the previous cases where the phase shift of this one is 0, and common collector followed by common collector also, we got the same phase shift. And the voltage gain for this one and this one is same 1, and for this one it's around 125, we got it. And current gain is also maximum. The input resistance for this one is we got it around 10 kilo ohms, and for this one is 1 kilo ohms. So the difference over here, if clearly observe the input resistance requirement point of view where it is maximum required, so 1 kilo ohm CE amplifier will not be suitable, 10 kilo ohms CC amplifier may be suitable, but where I need a maximum resistance of my circuit, where it offers that very less loading on the source, yes, when weak mic or weak source is connected, I prefer my circuit with high input resistance. That Darlington pair will be more suitable. So whatever the requirements that I am expecting and I wanted to get it, am I getting through the simulation or not? Let us verify. So coming to the simulation. So first of all, I will be checking my input and output waveform where like I'm giving a strong signal because the gain of this amplifier which we expect it is 1. So strong signal need not to generate, the transistor will not go into the active region for sure. So I will be giving a strong signal. I need not to worry about like a very weak signal need to be generated at the input. So easy way of like generating a strong signal from the function generator in the lab. So if I simulate it, so where so 2 into 3 divisions around 6 volts, 3 volts per per peak. So peak to peak is around 6 volts. So that is the 6 volts we got it at the channel A. And a similar way, in the similar way, in the channel B also 2 units per division, there will be 3 units, like around 6 volts we got it. So it's when you apply 6 volts at the input, I got it around 6 volts. So the gain offered by the circuit is almost 1. So this is what verified. This is what verified. And let's verify the phase shift also. So if I see this one, so input and output should be in the same phase to be verified by bringing that at on the 0 axis, at a DC level 0. So if I bring it on the same level, the input and output will be overlap on each other. So I can say the phase shift by input to the output is 0 degrees. So exactly how I got it, the phase shift 0 in the CC, I will be getting the phase shift again here in the Darlington also 0. So now we'll go with the another calculation of current again. What I do is to calculate the current again, what I do is I'll be keeping a ammeter notation over here at the input and ammeter notation at the output. So this is what my input branch and this is what my output branch. If I simulate it, so there will be input current of 324 nano. So 324 nano amperes input current, and there will be output current of 177 nano. 177 nano, sorry, 177 nano. 177 nano amperes, and output current will be 1.79 milli. 1.79 milli. So where if I calculate that current again, so 1.79 milli means 10 to the power of 10 to the power of 3, yes, 3, and 10 to the power of 3. So it will be converted into nano amperes by, so input current is around like 177. So now if you take it, so 179 by 177 into 10 to the power of 1 into 10 to the power of 3 nano. So this is also nano amperes. So this much gain I got it. Current gain this much I got it. So approximately this will be 1, and that will be 10 to the power of 4. So beta value which I chose it around 100. So now like I got it like 100 into 100. So it is nothing but a HFE whole square. So what I got it like beta times whole square or HFE times whole square, that much current gain which I expect. So through the simulation also I got the same. So the transistor which expects the beta times of IB has to flow here, and from this also it will be expecting beta times again, that also should flow. So 177 it will be multiplied by beta of this much, and beta again that much it has to flow. Then only like a current equations controlling the current equations by the transistor will be satisfied. Otherwise the transistors would have gone into the saturation region, so would have get output waveforms also distorted, so we will not get a faithful signal. So here we are getting a faithful signal means the transistors for sure it will be in the active region, there will be a control current of beta times will be flow for sure. So this is how I have calculated my current gain also. So now final thing where I like important thing, the thing is I have to calculate the input resistance, where my main requirement of Darlington pair is improving the input resistance to reduce the burden on the source, impedance matching at the source as well as load. So input resistance need to be improved. That's what my main interest. So where with the arrangement of two transistors connected over here, with the connection Darlington connection, I have to increase the resistance. I have to observe that increased resistance across that. So for that sake, I will be using a maximum power transfer theorem where like source impedance equal to load impedance, so which we have already used in the previous sessions where to calculate the input resistance, the same method let me follow. So I will be using a test resistance here. I will be using a test resistance over here, and what I do is I will be keeping some value here, 1 kilo if I keep it here, 1 kilo if I keep it here. So there is no need that channel B should see at this place. Even I see it over here also, no issue, because this amplifier will give the gain 1. So you take the signal of from this node or from this node will be the same. So I'm okay with taking the signal from the output directly instead of taking the signal over here. So now if I see my signal, so channel A and channel B, it will be same almost. But what we are expecting channel A, what we are giving is around 3 volts peak, in the sense 6 volts. So we are expecting 6 volts. So when I keep a resistance over here at this point, we are expecting 3 volts. So exactly 3 volts need to be dropped over here, and the 3 volts need to be dropped across my amplifier circuit. So 3 and 3, definitely this resistance will be equal to the resistance of my entire circuit. So I expect the 3 voltage over here, but I just observe the 3 voltage over here because that the same voltage will be dropped here and here. So I don't have any problem that monitoring the signal instead of here also. So now what I expect 3 voltage at the output. So I expect the 3 voltage, but what happening here? We are getting 6 volts itself. Input and output will be same. So it means like this resistance which I keep it is very weak. So most of the signal 6 volts is going over here to the amplifier. So now I have to make it strong. So as we know 684, that is the strength of the resistance. If you have to keep it, I just keep it to that same resistance. So we can do rest of the iterations also, but I wanted to go directly because I'm confident about like the resistance offered by 584, offered by Darlington pair. So we can do the rest of the cases also, but we'll go directly. So if I go with this one directly, so where I move my input to I shift out input up and shift output towards down. So input is 3 divisions into 2, 6 volts as it is. Output need to be, I have to verify, output is 1 unit. Yes, so almost it accommodated in 3 divisions with the strength of 1 volt per each division. So there will be the voltage across the output is, across this one is 3 volts now. So 3 voltage now. So we got 3 voltage that when I keep a resistance of this one, so resistance of this one, when the resistance of this one is 584 kilo ohms, right? Exactly I got 6 to 3 volts. So it means like this is the resistance offered by my input section of Darlington pair. So where it compared with the CE and with compared with the CC, so my input resistance of the Darlington pair is very high. So I can conclude that a Darlington pair will be most of the suitable component or a device where it can be connected with the source. So that impedance matching at the source will be mostly possible with the Darlington pair.